According to Institute of Electrical and Electronics Engineers Standard 110-2019 Section 7.10 concerning the protective conductor, or P, shall not be electrically connected to the neutral conductor, or N, except at the service entrance. The National Electrical Code, or NEC, Article 250.24 A5 states that the protective conductor, or P, shall not be connected to the neutral conductor, or N, within the building or structure. The reasoning is as follows. In the event that the P connection to the machine is lost, the N conductor becomes energized through the jumper to P in the machine control panel. This creates a potentially lethal shock hazard to anyone touching exposed metal parts of the machine or the neutral conductor itself. Consider this case study from the Electrical Safety Foundation International, or SC. A worker was fatally electrocuted when he touched the exposed metal frame of a machine that had lost its P connection. The N conductor was connected to P inside the machine's control panel, creating an energized path to the frame. Furthermore, an article from the National Electrical Contractors Association, or NECA, states if the neutral conductor is connected to the protective earth, or P, at the load, then the P conductor would become energized when the P conductor is accidentally disconnected. This could cause a shock hazard to anyone touching the exposed metal parts of the equipment. And finally, a report from the Workplace Safety and Insurance Board, or WSIB, of Ontario, Canada, states multiple incidents of electric shock and injury have occurred due to improper grounding of electrical equipment and connection of the neutral conductor to the protective earth conductor. Connecting the N conductor to P creates a serious safety hazard. By providing the N conductor to machines with aligned to neutral loads and removing the N to P connection, the risk of electric shock and injury can be significantly reduced. Let's delve deeper into the technical aspects of this safety issue, exploring the underlying principles and potential scenarios that can lead to hazardous conditions. Firstly, understanding the fundamental difference between the neutral and protective earth conductors is crucial. The neutral conductor is a current-carrying conductor that provides a return path for unbalanced current in a three-phase or single-phase system. It is intentionally grounded at the service entrance to establish a reference point and limit voltage to ground. In contrast, the protective earth conductor, or P, is a safety conductor that provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. It is connected to the exposed metal parts of equipment to ensure that they remain at or near ground potential under normal operating conditions, preventing electric shock. Secondly, when the neutral conductor is improperly connected to the protective earth conductor at the load, a parallel path for neutral current is created. Under normal conditions, a portion of the neutral current will flow through the P conductor back to the source. This can lead to several undesirable consequences, including 1. Increased current flow in the P conductor, potentially exceeding its ampacity and causing overheating or even fire. 2. Voltage drop along the P conductor, resulting in a difference in potential between the equipment frame and the grounding electrode system. 3. Increased electromagnetic interference, or ME, due to the circulating current in the ground loop. 4. Reduced effectiveness of ground fault protection, as the fault current may be diverted through the neutral to ground connection, bypassing the ground fault current transformer, or GFCT. In the event of a ground fault, such as a short circuit between a live conductor and the equipment frame, the fault current will flow through both the P conductor and the neutral conductor back to the source. If the P connection is lost or compromised, the equipment frame will become energized at a voltage level determined by the impedance of the neutral to ground connection and the magnitude of the fault current. This creates a significant shock hazard to anyone who comes into contact with the energized equipment. Moreover, even if the P connection is intact, the presence of a neutral to ground connection at the load can interfere with the proper operation of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small imbalances in current between the line and neutral conductors, indicating a ground fault condition. When a neutral to ground connection exists at the load, a portion of the fault current may return through the neutral conductor, reducing the current imbalance detected by the GFCI and potentially preventing it from tripping. To illustrate the potential hazards associated with neutral to ground connections at the load, consider the following scenarios. Scenario 1 involves a machine with a line to neutral load, such as a lighting fixture or control circuit. The neutral conductor is connected to the PE conductor inside the machine's control panel. The PE connection to the machine is accidentally disconnected or becomes corroded, resulting in a high impedance connection. A fault occurs in the line to neutral load, causing current to flow through the neutral conductor and back to the source. Since the PE connection is compromised, the equipment frame becomes energized at a voltage level determined by the impedance of the neutral to ground connection and the magnitude of the fault current. A worker touches the energized equipment frame and receives an electric shock. Scenario 2 involves multiple machines connected to the same electrical panel. Each machine has a neutral to ground connection at the load. A ground fault occurs in one of the machines, causing current to flow through the PE conductors of all the machines. Due to the neutral to ground connections at each machine, a circulating current is established in the ground loop, leading to increased electromagnetic interference and potential overheating of the PE conductors. In addition, the ground fault current may be diverted through the neutral to ground connections, reducing the effectiveness of ground fault protection. To mitigate the risks associated with neutral to ground connections at the load, the following measures should be implemented. Firstly, the neutral conductor should not be connected to the PE conductor at any point beyond the service entrance. This ensures that the PE conductor remains a dedicated safety conductor and does not carry normal neutral current. Secondly, machines with line to neutral load should be provided with a dedicated neutral conductor that is run back to the electrical panel. This eliminates the need for a neutral to ground connection at the load. Thirdly, the PE conductor should be properly sized and installed in accordance with the National Electrical Code, or NEC, to provide a low impedance path for fault current. Fourthly, regular inspections and testing should be conducted to ensure the integrity of the PE connections and the proper operation of ground fault protection devices. Fifthly, electrical workers should be properly trained in the principles of grounding and bonding and the hazards associated with improper wiring practices. In addition to these measures, it is important to consider the specific requirements of the applicable electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding of electrical systems, including specific provisions for separating the neutral and grounding conductors. The Institute of Electrical and Electronics Engineers, or IEE, also publishes standards on grounding and bonding, such as IEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, commonly known as the Green Book. These standards provide guidance on the design, installation, and maintenance of grounding systems to ensure electrical safety. Furthermore, it is essential to understand the role of bonding in preventing electric shock hazards. Bonding refers to the practice of connecting all non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. This includes the equipment frames, metal conduits, enclosures, and other metal components. When all metal parts are properly bonded together, they will be at or near the same potential, minimizing the risk of electric shock in the event of a ground fault. The National Electrical Code, or NEC, requires that all metal parts of an electrical system be bonded together using approved bonding methods such as bonding jumpers, bonding screws, or listed bonding connectors. The bonding conductors must be sized in accordance with the NEC based on the size of the circuit conductors. In addition to preventing electric shock hazards, proper grounding and bonding also play a crucial role in protecting sensitive electronic equipment from damage due to voltage surges and transients. Voltage surges can occur due to lightning strikes, utility switching operations, or other disturbances on the power system. These surges can damage or destroy electronic equipment if they are not properly suppressed. Grounding and bonding provide a low impedance path for surge current to return to the source, diverting the surge energy away from sensitive equipment. Surge protective devices, or SPDs, are often used in conjunction with grounding and bonding to provide additional protection against voltage surges. SPD are designed to clamp the voltage to a safe level, preventing damage to connected equipment. It is important to select SPD that are properly rated for the application and to install them in accordance with the manufacturer's instructions. In conclusion, connecting the neutral conductor to the protective earth conductor, the load creates a serious safety hazard that can lead to electric shock, equipment damage, and other undesirable consequences. By providing a dedicated neutral conductor to machines with line to neutral loads, removing the neutral to ground connection, and implementing proper grounding and bonding practices, the risk of electrical hazards can be significantly reduced. It is essential to consult with qualified electrical professionals and to adhere to the requirements of the applicable electrical codes and standards to ensure the safety and reliability of electrical systems. Remember, electrical safety is paramount, and taking the necessary precautions can prevent accidents and save lives. Proper grounding and bonding are not just code requirements, they are essential safety measures that protect people and equipment from the hazards of electricity. Let's explore some additional considerations related to this topic. Firstly, it's important to differentiate between grounding and bonding. Grounding refers to connecting an electrical system to the earth, typically through a grounding electrode system consisting of ground rods, ground plates, or metal water pipes. Bonding, on the other hand, refers to connecting non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. While both grounding and bonding are important for electrical safety, they serve different purposes. Grounding establishes a reference point for the electrical system and limits voltage to ground, while bonding ensures that all metal parts are at or near the same potential, minimizing the risk of electric shock. Secondly, it's crucial to understand the concept of impedance in grounding and bonding systems. Impedance is the total opposition to current flow in an alternating current circuit, including resistance and reactance. A lower impedance path for fault current is essential for the proper operation of overcurrent protective devices and for minimizing voltage rise on equipment frames during a ground fault. The impedance of a grounding and bonding system is affected by several factors, including the size and material of the conductors, the length of the conductors, the number of connections, and the presence of any discontinuities or corrosion. To ensure a low impedance path, it's important to use appropriately sized conductors, minimize the length of the conductors, make sure that connections are clean and tight, and protect the conductors from corrosion. Thirdly, it's important to consider the impact of harmonics on grounding and bonding systems. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads such as electronic ballast, variable frequency drives, and computers. Harmonics can cause increased current flow in neutral conductors, overheating of transformers, and malfunctioning of electronic equipment. To mitigate the effects of harmonics, it's important to use harmonic filters, oversized neutral conductors, and dedicated grounding systems for sensitive electronic equipment. Fourthly, it's important to understand the requirements for isolated ground systems. Isolated ground systems are used in sensitive electronic equipment to minimize noise and interference. In an isolated ground system, the grounding conductor for the equipment is isolated from the building's grounding system and is connected directly to the grounding electrode system. The National Electrical Code, or NEC, has specific requirements for isolated ground systems, including the use of an insulated grounding conductor and the prohibition of any connection between the isolated ground conductor and the building's grounding system. Fifthly, it's important to consider the requirements for equipotential bonding in areas with sensitive electronic equipment, such as hospitals and data centers. Equipotential bonding involves connecting all metal parts in an area together to create an equipotential plane, minimizing the potential difference between any 2 points in the area. This helps to prevent electric shock hazards and to protect sensitive electronic equipment from damage due to voltage surges and transients. The National Electrical Code, or NEC, has specific requirements for equipotential bonding in certain types of occupancies, such as hospitals and swimming pools. Sixthly, it's important to consider the requirements for grounding and bonding in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present, creating a risk of explosion or fire. The National Electrical Code, or NEC, has specific requirements for grounding and bonding in hazardous locations to prevent the accumulation of static electricity and to ensure that any fault current is safely conducted back to the source. These requirements include the use of explosion-proof enclosures, intrinsically safe circuits, and special grounding and bonding methods. Finally, it's important to remember that grounding and bonding are not one-size-fits-all solutions. The specific requirements for grounding and bonding will vary depending on the type of electrical system, the type of occupancy, and the applicable electrical codes and standards. It's essential to consult with qualified electrical professionals and to perform a thorough analysis of the electrical system to determine the appropriate grounding and bonding methods. In addition to these technical considerations, it's also important to address the human factors aspects of electrical safety. Electrical workers should be properly trained in the principles of grounding and bonding and the hazards associated with improper wiring practices. They should be provided with the necessary personal protective equipment, or PPE, such as insulated gloves, safety glasses, and arc flash suits, to protect themselves from electrical hazards. They should also be encouraged to follow safe work practices, such as de-energizing equipment before working on it, using lockout-tagout procedures, and verifying the absence of voltage before touching any electrical conductors. Furthermore, it's important to promote a culture of safety in the workplace. Management should demonstrate a commitment to electrical safety by providing the necessary resources, training, and equipment to ensure that electrical work is performed safely. Employees should be encouraged to report any electrical hazards or unsafe conditions without fear of reprisal. Regular safety meetings and audits should be conducted to identify and address potential electrical hazards. By addressing both the technical and human factors aspects of electrical safety, we can create a safer working environment and prevent electrical accidents. Let's delve into the specifics of how to properly address this situation, keeping in mind the applicable codes and standards. Firstly, a qualified electrician should perform a thorough inspection of the electrical system to identify any existing neutral to ground connections at the load. This inspection should include visual examination of the wiring and connections, as well as electrical testing to verify the integrity of the grounding and bonding system. Secondly, any existing neutral to ground connections at the load should be removed. This may involve disconnecting the neutral conductor from the equipment frame or from the grounding conductor. Thirdly, a dedicated neutral conductor should be installed for each machine with line to neutral loads. This neutral conductor should be run back to the electrical panel and connected to the neutral bus. Fourthly, the grounding conductor for each machine should be properly sized and installed in accordance with the National Electrical Code, or NEC. The grounding conductor should be connected to the equipment frame and to the building's grounding electrode system. Fifthly, the grounding and bonding system should be tested to verify that it meets the requirements of the National Electrical Code, or NEC. This testing should include impedance testing to ensure a low impedance path for fault current and continuity testing to verify that all metal parts are properly bonded together. Sixthly, all electrical work should be performed by qualified electricians who are familiar with the National Electrical Code, or NEC, and other applicable codes and standards. The electrician should follow safe work practices and use appropriate personal protective equipment, or PPE. Seventhly, documentation should be maintained of all electrical work performed, including the results of inspections and testing. This documentation should be kept on file and made available for future reference. In addition to these specific steps, it's also important to consider the overall design and maintenance of the electrical system. The electrical system should be designed to minimize the risk of ground faults and to provide adequate protection for people and equipment. Regular maintenance should be performed to ensure that the electrical system is in good working order and that any potential problems are identified and addressed promptly. This maintenance should include periodic inspections, testing, and cleaning of electrical equipment. Furthermore, it's important to stay up to date on the latest electrical codes and standards. The National Electrical Code, or NEC, is revised every 3 years, and it's important to be aware of any changes that may affect the design, installation, or maintenance of electrical systems. Continuing education and training are essential for electrical professionals to stay current on the latest codes and standards and to maintain their skills and knowledge. By following these recommendations and adhering to the applicable codes and standards, it's possible to significantly reduce the risk of electrical hazards and to ensure the safety and reliability of electrical systems. Remember, electrical safety is a shared responsibility, and everyone has a role to play in preventing electrical accidents. Let's reinforce this information with a few additional points. The practice of connecting the neutral to ground at the load side of the service equipment creates what is known as a parallel neutral ground path. This is problematic for several reasons. Firstly, it can cause unwanted current flow on the grounding conductors. The grounding conductors are intended to carry fault current only, not normal load current. When a neutral to ground connection exists at the load, a portion of the neutral current will flow through the grounding conductors back to the source. This can lead to increased voltage drop on the grounding conductors, increased electromagnetic interference, and potential overheating of the grounding conductors. Secondly, a neutral to ground connection at the load can interfere with the operation of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small imbalances in current between the line and neutral conductors, indicating a ground fault condition. When a neutral to ground connection exists at the load, a portion of the fault current may return through the neutral conductor, reducing the current imbalance detected by the GFCI and potentially preventing it from tripping. Thirdly, a neutral to ground connection at the load can create a shock hazard. If the grounding conductor is accidentally disconnected or becomes corroded, the equipment frame can become energized at the neutral voltage. This can create a potentially lethal shock hazard to anyone who comes into contact with the energized equipment. To prevent these problems, the National Electrical Code, or NEC, prohibits the connection of the neutral to ground on the load side of the service equipment. The only point where the neutral and grounding conductors are permitted to be connected is at the service equipment. This ensures that the grounding conductors only carry fault current and that GFCIs can operate properly. It also minimizes the risk of electric shock by ensuring that the equipment frame is always at or near ground potential. In addition to the NEC requirements, there are also industry best practices for grounding and bonding. These best practices include using appropriately sized grounding conductors, minimizing the length of the grounding conductors, making sure that connections are clean and tight, and protecting the grounding conductors from corrosion. It's also important to perform regular inspections and testing of the grounding and bonding system to ensure that it is in good working order. These inspections and tests should include visual examination of the wiring and connections, as well as electrical testing to verify the integrity of the grounding and bonding system. By following these best practices, you can further reduce the risk of electrical hazards and ensure the safety and reliability of electrical systems. Remember, electrical safety is not just a code requirement, it's a moral obligation. We have a responsibility to protect ourselves and others from the hazards of electricity. By understanding the principles of grounding and bonding and by following safe work practices, we can create a safer working environment and prevent electrical accidents. Always consult with a qualified electrician if you have any questions or concerns about electrical safety. They can provide expert advice and guidance to ensure that your electrical system is safe and code compliant.